Every once in a while, the universe snaps. A surge of magnetic fury erupts from a star's surface, a distant supergiant collapses under its own weight, and deep within the heart of a spinning neutron star, unimaginable pressures unleash torrents of energy that ripple across space and time. These are cosmic tipping points, moments when the universe teeters on the edge of chaos, where the forces that create worlds can also destroy them in an instant. Everything in existence, planets, stars, galaxies, and even life itself, balances on a razor-thin line between stability and collapse. Push any system too far, and nature responds with cataclysm. Yet, in the midst of destruction, the universe has a way of finding equilibrium. Hidden within the chaos are invisible safeguards, subatomic mechanisms that fight to restore order, allowing matter to endure when it should have perished. Nowhere is this balance more extreme, or more mysterious, than inside neutron stars, the densest, strangest, and most unforgiving objects in the cosmos. Neutron stars are what remain after the death of massive suns, tiny, city-sized remnants so heavy that a single teaspoon of their material weighs as much as a mountain. Their gravity is beyond comprehension, a falling object would strike their surface at half the speed of light, yet even here, the star's structure resists total collapse. As we dive deeper through their impossible layers, we confront matter at its most exotic, crushed into forms unseen anywhere else in the universe. At their cores may lie the key to understanding not just the death of stars, but the very nature of reality itself. To uncover this mystery, we must first look back, into the fiery heart of our own Sunday. While the Parker Solar Probe streaks through space at 200 kilometers per second, daring to graze the sun's scorching atmosphere, scientists on Earth trace the origins of solar power back to the work of early 20th century physicist Meghnad Saha. His groundbreaking ionization equation revealed that the sun's light and heat are born from the delicate balance between matter and energy. Beneath its blazing surface, hydrogen atoms are crushed and fused into helium, releasing energy that pushes outward, countering gravity's endless pull. This equilibrium, known as hydrostatic balance, is what keeps stars alive. Yet nothing lasts forever. One day, the sun's fuel will run dry, and the scales will tip. For stars much larger than ours, this moment triggers a spectacular collapse, a supernova, so powerful that for a brief instant, it outshines entire galaxies. The collapse compresses the core into an unimaginable density, where quantum laws replace classical physics. Here, gravity is met by a new, invisible resistance, degeneracy pressure, a quantum force discovered by Ralph Fowler and later expanded by Subrahmanyan Chandrasekhar. This force keeps white dwarfs stable and paves the path to the even denser neutron stars. These discoveries were the first glimpses of matter at its limit, where particles are stacked so tightly that quantum mechanics itself holds back the abyss. It's a precarious existence, one that defines neutron stars and the forces within them. When we study these remnants of stellar death, we aren't just exploring astrophysics, we're testing the boundaries of physics itself. From the sun's glowing heart to the remnants of exploded giants, every star walks the same tightrope between creation and collapse. And somewhere out there, spinning silently in the dark, neutron stars remind us that even in a universe built on chaos, balance, no matter how fragile, always finds a way. At the heart of the Crab Nebula lies one of the universe's most extraordinary objects, a neutron star. If white dwarfs seemed impossibly dense, neutron stars push that limit to the extreme. They are 100 million times denser, meaning a single tablespoon of neutron star matter would weigh more than the combined mass of all humans who have ever lived. While white dwarfs are Earth-sized, neutron stars are barely 21 kilometers across, roughly the size of London, yet they pack in more mass than our sun. The gravity on their surface is unimaginable. To escape Earth's pull, one must travel at 11 kilometers per second, but to leave a neutron star requires speeds of 150,000 kilometers per second, nearly half the speed of light. Even mountains cannot exist there as they do on Earth. The tallest peaks on a neutron star are less than a millimeter high, making them the smoothest objects in the cosmos. Many of these stars spin at incredible speeds, with the Crab's neutron star rotating 30 times every second, while others can spin hundreds of times per second. Their magnetic fields are also extreme, about 100 billion times stronger than that of a refrigerator magnet, and they channel radiation from their poles that we detect as pulses, giving rise to their name, pulsars, short for pulsating stars. The formation of neutron stars follows a catastrophic chain of stellar death. When a dying star's core exceeds 1.4 times the mass of the Sun, the Chandrasekhar limit, it collapses further, forcing electrons and protons to fuse into neutrons. This creates a neutron star, held up only by neutron degeneracy pressure, the last line of defense against total collapse. Yet even neutron stars aren't pure neutrons. The deeper we go, the more mysterious their composition becomes. To understand their inner structure, scientists have turned to the NICER telescope aboard the International Space Station, a washing machine-sized X-ray instrument delicately repaired in orbit in 2025 after damage from solar exposure. NICER has begun revealing tantalizing clues about the exotic layers within neutron stars, from diamond-dense atmospheres to the strange theoretical material called nuclear pasta, twisted configurations of protons and neutrons possibly 10 billion times stronger than steel. These structures, shaped like gnocchi, spaghetti, and lasagna, make up a crust weighing more than 3,000 Earths. In 2019, NICER observed something that challenged all expectations, a neutron star named J0740 plus 6620. It was one of the most massive ever discovered, over twice the mass of the Sun, yet it wasn't smaller as theory predicted. This anomaly sparked debate about the equation of state that governs how matter behaves under such pressure. Some scientists suggested the core might be less squishy than expected, perhaps influenced by new physics or even dark matter. As stars move through space, they might absorb dark matter, which sinks to their cores and strengthens their resistance to gravity. Others propose that the interior could be made of Bose-Einstein condensates, a new state of matter where particles called bosons move in unison, providing extra outward pressure to stabilize the star. Such neutron stars might, in fact, be Bose-Einstein condensate stars, a concept inspired by the work of Indian physicists Satyendra Nath Bose and Albert Einstein in the early 20th century. But even neutron stars have their limits. In 1939, George Volkoff and Robert Oppenheimer calculated the Tolman-Oppenheimer-Volkoff (TOV) limit, which defines the maximum mass a neutron star can have before collapsing further, somewhere around 2.2 to 2.9 solar masses. Beyond this threshold, even neutron degeneracy pressure cannot save the star. In 2017, the LIGO Observatory detected gravitational waves from two colliding neutron stars in the galaxy NGC 4993, marking the dawn of multi-messenger astronomy. This event, named GW170817, helped refine the TOV limit and revealed that when neutron stars merge and exceed this mass, they either form a quark star, a body made of disassembled quarks, or collapse completely into a black hole. Black holes represent the final tipping point, where gravity wins entirely, crushing matter into an infinitely small singularity where time and space cease to exist. Yet, neutron stars remain crucial in testing the boundary between Einstein's relativity and quantum mechanics, two theories that cannot both be fully correct. Recent observations of unexpectedly cold neutron stars in 2024 by Alessio Marino's team have even ruled out several possible equations of state and theories of quantum gravity. Neutron stars are, in essence, cosmic laboratories, where the universe tests the very limits of physics. They are relics of stellar death yet key to understanding the nature of matter, energy, and space itself. Nearly a century after their existence was first proposed, they remain among the most mysterious and awe-inspiring objects ever discovered, dense, dazzling, and defiant against the pull of the abyss.